Hello everyone, welcome to my channel. This is Leo and let's do some more Leetcode problems today. So today's problem is called Trapping Rainwater 2. We were given an n by n integer matrix height map representing the height of each unit cell in a 2D elevation map. We were asked to return the volume of water it can trap after raining. So intuitively, if we want to trap some water inside something, we have to have a wall-like thing on the surrounding, right? So this is pretty intuitive for this problem. If we have a cell that is its height is less than the neighboring cells, it cannot hold any water. But if we go inside, if this cell, its height is less than all of its neighboring cells, it can hold unit of water. And how many units of waters it can hold depends on the height difference between itself and all of its neighbors, okay? Or to say the lowest of all of its neighbors. So this becomes pretty intuitive. So we can traverse from the edge, from the smallest height to the higher one, to the higher one, to the highest one, and go from there to the inside. If we find a difference, we can add how much water I can save to the final result. Okay? In that case, we can calculate how much water we can save. So this is a pretty easy representation of the problem. So how do we do this? What kind of data structures can we use? There are three variables needed, which is m, which is n, and the height. So I think we may need a new data structure to represent each cell with its coordinates and its height. So with the height, we can first traverse from the edges to the middle, to the internal areas that we can traverse from the smallest height one, right? And if it can go inside and it can find a neighbor which height is lower than itself, that means we can hold some water in here, okay? So how do we effectively find all the cells with the minimum heights? We're thinking of a heap data structure, okay? So first, to store the information of each element, we're going to use a data structure. Let me call it cell. So it involves row, it involves column, and also involves height, okay? And the cell, we can write the constructor here. This dot row equals to row, this dot column, and this dot height, okay? So let's do some sanity checks first, okay? So first, sanity check. If it's null, if its length is 0, or if its columns is 0, we will have nothing to return, okay? The second thing is, since we're using a priority queue to store all the cells in it, we're going to initialize the priority queue. Okay, so priority queue, we're going to store all the cells in it. And what's the rule for this? We're going to sort it by its height from the minimum to the maximum. So I will use a lambda function to solve this. The cell with the lower height will be given more priority to this, okay? So after that, we have a queue, and we're going to go with a BFS traversal. So we're gonna initialize the BFS. But before that, we need to have some elements in our priority queue. So as I said, we're going to add all the edge cells into the priority queue. So add edge cells into the priority queue. So I will record its dimensions. All right. And I will have a visited matrix to record its whether it's been visited or not. Okay. And now I'm going to populate the queue with the cells. And PQ will add new cell. So M, we're going to record the first, so to speak, the first column. And the height, right? So the height would be height map I0, okay? Here we'll also add new cell I and n-1. Also, we will add it to the set the visited matrix to true, okay? I0 to true and visited I n-1 to true, okay? Same for the up and down rows. PQ will add new cell. So 0 I height map 0 I. PQ dot add new cell n-1 I n-1 I. 0 I to true and n-1 I to true. Okay. Yeah. And then we can start our BFS. First, we need a result to record all the water I can save from this, and I can initialize the BFS. So we have a cell. PQ.pull. So now we have the cell with the lowest height. Okay. So what do? We go through all of its neighbors to see how much water we can save, right? So for all of its neighbors, I think the first one will be -1, 0, and 0, 1, 1, 0, and 0, 1, and also 0, -1. Okay, for all of its neighbors, I will record like cell.row plus direction 0. C will be cell.column plus direction 1. Okay. If the neighboring cell is inbound and unvisited, I can add it to our queue. Okay. If R is larger than or equal to 0 and R is less than M, C larger than or equal to 0, C is less than R, sorry, C is less than N and unvisited. Oh, what am I spelling it? Okay, now we are at the neighboring cell. And when do we put it into our priority queue? We just put it in there, right? But what do? First, we mark that as visited equals to true, and we will see how much water we can use for this step, right? So result will add, if like I said, if the current height is less than the neighboring height, we will get a negative number for this. So in this case, we will just add nothing. So we need a ceiling for that. That's 0, okay? Cell.height minus height map RC, which is the height of the neighboring cell, okay? And we can add the neighboring cell to our priority queue. So we can add a new cell with its RC and the height. So if we really can save some water, do we record its, like for example, we're expanding the BFS from this cell to this cell. I think we can add something to the result since the current height is higher than the neighboring height, right? But if we put this into our queue, do we record its real height or the height of the surface of the water? I think we have to start from the surface of the water so that we can know, oh, it can go deeper, right? So we do, in that case, we don't have any duplicate calculations. So we have to use a math.max, or it's either height map RC or cell.height. This is the surface of the water. Okay, let's see which one is higher for that, and we can go from there. Yeah, after this, I think we're ready to go. It should be ready. Okay, let's see. Yeah, I think it passes the test cases. And let's analyze the complexities for this. So for time complexity, if we take n by n, I think we will traverse every cell in there, which is mn. And in every operation, I think we have to pop from the priority queue. That gives us a extra of log mn. Okay, that should be the worst case. And for the space complexity, it's going to be mn because we have a Boolean matrix here, m by n, and the worst case, the priority queue can contain everything of the original height map. Yeah, so let's submit it. And we got a pass. Thank you so much for watching. I'll see you in our next video.